This video is part of the Periodic Trends series, and it will focus on ionization energy. So what is ionization energy? It's the energy required to form an ion. And how do we form an ion? In order to form an ion, an atom must gain or lose electrons. But to come up with a definition for ionization energy, we had to pick one. So ionization energy is defined as the energy required to remove an electron from an atom. When looking at the periodic table, ionization energy increases going up a group. So why is that the case? Let's examine this diagram. If you pick a group on the periodic table and look at it from bottom to top, what changes? Notice how the nucleus is closer to the valence electrons as we move up the group. And just so everyone's clear, the red energy level represents the outermost energy level where the valence electrons are. The gray energy levels, so here and here, they represent the part of the cloud, part of the electron cloud, where the core electrons are. So not the valence electrons. So again, as we go up the group, notice how the nucleus gets closer and closer to the valence electrons. The size of the atom is smaller as we go up the group. And because the valence electrons are closer to the nucleus, due to the fact that there are fewer core electrons, the outer electrons are not as shielded. So there's less shielding as you go up a group. So the outer electrons are not as shielded as you go up a group from the nucleus as the ones closer to the bottom are. When the nucleus is close to the outer electrons, the attractive force that the nucleus is able to exert on the valence electrons increases. So it becomes more difficult to remove a valence electron from the atom. So that's why we say as we go up a group, the amount of ionization energy required to remove an electron increases. As we go across a period from left to right, so just follow the arrow that's shown here. When we go left to right, notice that it says here in the diagram, first ionization energy increases. So let's talk about why. When we go across a period from left to right, notice the size of the atom. The atomic radius is decreasing. And look at what's increasing, the number of protons. Lithium is a group 1 metal. This is group 1. Beryllium is a group 2 metal. Boron is in group 3A, or you could say 13. Carbon is in group 4A or group 14. Nitrogen is group 5A or 15. There's oxygen and there's fluorine. So as we go across a period from left to right, the number of protons increases. Notice how lithium has 3 protons, and then when you go to the next element, you have 1 more proton added. So as we go all the way across, notice how fluorine has 9 protons. Fluorine, because it has 9 protons, has a greater effective nuclear charge. It's got a stronger nucleus because it has more protons in it. And as a result, because it has a greater effective nuclear charge, it's more difficult to remove an electron from fluorine. So the greater the effective nuclear charge, the more energy is required to remove a valence electron. So that's why when we go left to right across a period, ionization energy increases. This periodic table shows you the first ionization energy values for each element. The values are shown in units, kilojoules per mole. Kilojoules is a unit of energy. That's how we use joules, kilojoules, calories to express units of energy. So ionization energy is most often expressed in kilojoules per mole. See if you notice the pattern. We're looking at the general trend. So generally, when we go left to right in a period, notice how the ionization energy value increases, okay? And then also when you go up a group, notice again how the ionization value increases. Let's take, for example, francium. Francium's ionization energy is 380 kilojoules per mole. Versus, if we're looking within the same group, hydrogen. Hydrogen's ionization energy is 1,312 kilojoules per mole. See how that's significantly higher? Also, take note, francium is a metal. What do we know about metals? Do metals gain or lose electrons in order to achieve that stable octet, in order to achieve stability, the stable configuration that noble gases have? Metals in group 1, remember, they lose electrons. They'll lose one electron so that they can become stable, like noble gases. So metals in general have low ionization energies compared to nonmetals. Hydrogen is a non-metal, so that's why its ionization energy is greater. Now, if we look at the extreme opposite end of the periodic table, let's take helium. Helium's first ionization energy is 2,372.3 kilojoules per mole. This is how much energy it will take to remove one electron from helium. Helium, like the other noble gases, is already stable. It does not want to readily lose an electron, because it's already stable. So in order to remove an electron from a noble gas or from the nonmetals in general, it's going to require a lot of energy. Now, remember, the nonmetals like fluorine, like oxygen, like nitrogen, how do they become ions? They become ions by gaining electrons. Remember the oxidation numbers? Nitrogen, when it forms an ion, is typically -3 in its oxidation value. Oxygen, when it forms an ion, is typically -2. And then fluorine, this whole family, is typically -1. Those are the oxidation numbers. So that's the number of electrons that they need to gain to achieve that stable octet. They don't want to lose electrons. A high ionization energy value then indicates a strong hold of the atom on its electrons. The higher that value is, the less likely those elements will form cations. And remember, cations are the positively charged ions. This is the same periodic table we were just looking at. So to give you a little memory trick to remember that ionization energy increases when you go up a group and when you go to the right in a period, we can say that ionization energy follows the ice cream cone principle. Notice how the size of the ice cream, the width of it, it's bigger up here, and then the bottom of it is smaller. So similarly, ionization energy is larger. the value is larger up at the top of a group and smaller at the bottom of the group. The same thing applies if we were to knock over the ice cream cone. If we knock over the ice cream cone, you need to knock it over to the right. Okay? When you knock it over to the right, the same principle applies. The ionization energy is larger at this end of the periodic table. It's larger up here on this side. This is where the nonmetals are, and smaller on the left side. The periodic table we were looking at previously showed us the first ionization energy values. That is the amount of energy needed to remove one electron from an atom. This table shows you the first values here, but it also shows you the second and third ionization energies. So the second ionization energy is shown here. I'm color coding it for you in green, and the third ionization energy is shown here in blue. And then it continues on to show you the fourth all the way through the seventh ionization energies for each of these elements. So let's take a look at what this actually means. What do you notice about the elements listed? What do they have in common? Did you notice that these elements here are all from period 3? These are period 3 elements. So let's take a look at each one. Sodium is a group 1 element. That means it has 1 valence electron. Magnesium is a group 2 element, an alkaline earth metal. It has 2 valence electrons. Aluminum is in group 13. It has 3 valence electrons. Silicon's in group 14, so 4 valence electrons. Phosphorus has 5 valence electrons, sulfur has 6, chlorine has 7 because it's a halogen, and finally argon's a noble gas and has 8. So let's take a look at the ionization energies required to remove electrons from these elements. So since sodium has 1 valence electron, it will form a positive 1 ion to achieve that stable octet, to achieve that noble gas configuration. So if you look at the value of the first ionization energy, it's quite low, 495 kilojoules per mole. But if you try to remove another electron from sodium, now you're taking away an electron from sodium's core. Notice the jump in energy. It goes from 485 kilojoules per mole to take 1 electron, all the way to 4,560 kilojoules per mole to take a second electron. And that's because now you're in the core electrons. Let's take a look at the other end of the periodic table, chlorine. Chlorine is an element that wants to gain electrons. Specifically, it wants to gain 1. So it will have a charge of -1, an oxidation number of -1, so it can become stable like the noble gas argon in its electron configuration. So chlorine doesn't want to lose any electrons at all. If you recall the dot structure for chlorine, chlorine has 7 valence electrons. There's 1 empty spot left right here. This is where the electron that chlorine wants to gain will go. Now, to remove one of these orange dots, one of these orange electrons from chlorine's valence electrons, it would take 1,255 kilojoules per mole of energy to remove one of these orange dots. To remove another one, it would take 2,295 kilojoules per mole. And notice how the energy, it continues to increase. So it's going to get progressively harder to remove more and more electrons from chlorine. If you look at argon, argon's got the greatest ionization energy because remember, argon already has its stable octet. So to remove an electron from a noble gas will require a large amount of energy. If we go back and take a look at the second metal, magnesium, that's listed here, a group 2 metal, magnesium has 2 valence electrons, 1 and 2. So to lose the first electron, it's going to require 735 kilojoules per mole of energy. To lose a second electron, it will take more energy, 1,445. But still, these are just the valence electrons that we're losing. If we lose a third, now we're into magnesium's core electrons, and notice the jump in energy that's required to remove a third electron from magnesium. If we look at aluminum, aluminum has 3 valence electrons, so magnesium had 2, aluminum has 3. This is its dot structure, Lewis dot structure, 1, 2, 3. These are all valence electrons. To remove the first one, it would take 580 kilojoules. To remove the second one, 1,815. To remove the third one, 2,740. These are all valence electrons that are being removed. After they've been removed, now you're into the core. To take electrons away from an already stable core, that will require an enormous amount of energy. Now that we've talked about ionization energy, let's do some practice problems. So before we begin, just remember that the trend increases going up a group and going to the right in a period. So let's take a look at our first example. Which element has the largest ionization energy? Lithium or sodium? So lithium and sodium are both group 1 metals. Here they are. And hopefully you picked lithium as your answer. So remember, lithium has only 2 energy levels. So it's compared to sodium's 3. Its valence electrons are going to be closer to the nucleus. So the nucleus will exert a greater force of attraction on the valence electron that lithium has, pulling it closer. Our next example involves halogens, bromine and fluorine. So bromine and fluorine are right over here. Which element has the largest ionization energy? Hopefully you realized it was fluorine. And it's for the same reason. Fluorine has a nucleus that is closer to the valence electrons. Its nucleus then exerts a stronger attractive force on those valence electrons, pulling them closer in. Bromine's valence electrons are on the 4th energy level. It's in period 4. So the nucleus is unable to exert as strong of a force of attraction on those outer electrons. Now let's look at barium and polonium. So barium's right over here in group 2, and polonium is also in the same period, period 6, same period as barium. So which of these two has the largest ionization energy? The answer is polonium. So because barium and polonium are in the same period, we can't rely on the number of energy levels to explain our answer. Instead, we look at the number of protons each of these elements has. If you look up the atomic numbers on the periodic table, barium has 56 protons, and polonium has 84 protons. So because polonium has a higher effective nuclear charge, because the effective nuclear charge is greater than barium's, it is able to exert a stronger force of attraction on the valence electrons, pulling them closer in. And as a result, even though polonium and barium are both metals, it's going to require more energy to take away an electron from polonium than it is from barium, due to that difference in effective nuclear charge, due to that difference in the number of protons in its nucleus. Now let's take a look at our last example. Place the following in order of decreasing ionization energy. So think about what this word means, decreasing. Are we going from the highest energy to the lowest energy to the highest energy? So decreasing means we're looking at the element with the highest ionization energy and ending with the element with the lowest ionization energy. So chlorine, iodine, fluorine, bromine, acetine, do you see that they all come from the halogen family? So we're looking at these elements here. So what we want to do is identify the element that has the largest ionization energy in this family. So if we understand that the trend increases for ionization energy when you go to the right and when you go up, you can see fluorine is the element that's the furthest up. But the better explanation as to why the ionization energy of fluorine is the greatest is due to the fact that its valence electrons are closer in proximity to its nucleus. The positive attractive force of the nucleus allows it to exert a greater force of attraction on its valence electrons, making it more difficult to remove an electron. On the extreme opposite end, astatine would have the lowest ionization energy because its valence electrons are the farthest away from the nucleus. So if we rank our elements on this list, fluorine would be the highest in ionization energy, followed by what's right underneath it, chlorine. So followed by chlorine, so fluorine, then chlorine. Then underneath chlorine, we have bromine, and then we have iodine, and then finally astatine.